So the first thing that I want to say to you about chapter 4 is that the way that I run my class in here is that this chapter will be what I call a standalone chapter, meaning when we take our next test, which is I have no idea when, okay, so relax, it will be on chapter 4 only. It's not going to be combined with another chapter. Okay? So chapter 4 is all about solutions. It's a lot of vocabulary. There's some math in there. And I would say some of this chapter will be review and some of it will be new. So as I said, guys, there's a lot of vocabulary in this chapter. Most you probably remember. Okay, so we're talking about solutions. That's just a synonym for the term homogeneous mixture. A mixture, a physical combination of things, uniform composition, okay? And a solution is going to contain a solute and a solvent, all right? Solute is the thing that is being dissolved. You put the solute into the solvent, okay? Anytime I use the word soluble, okay, like table salt is soluble in water, all I'm really saying is it will dissolve. What is the opposite of soluble? Insoluble, yeah. So table salt is soluble in water, but it will be insoluble in, let's say, oil, for example. Okay? And for the most part, we're going to be dealing with aqueous solutions. Now, what does that word mean? Water is the what? Solvent. Okay, water is the solvent. Okay, and sometimes water is referred to as the universal solvent, meaning that it can dissolve most solutes. Not all, but most. And I want to tell you why that is. Okay, so this is a picture, a model of a water molecule. It has that bent shape. It's a covalent compound. Okay, and water is such a good solvent. Okay, not only because it's just readily available on Earth, but because it is polar. Okay, now that's a word that we need to review. Okay, you definitely learned it in Chem 1, but let's just revisit. The word polar, okay, means an uneven distribution of charge. So one side of the molecule would be a little bit more negative, the other side would be a little bit more positive. Now let's see if you remember a certain term. If I say to you that one element is more electronegative than another, do you remember what that means? Absolutely. Okay, electronegative means a very electronegative element, means an element that pulls electrons towards itself very well. Okay, so for example, in this model, let me change colors here. Okay, this is your oxygen. These are your two hydrogens. Okay, oxygen is the more electronegative element. Right, so this side of the molecule, the oxygen side, is going to be a little bit more negative, and the hydrogen side is going to be a little bit more positive. Okay, but that makes water a very good solvent. Okay, it allows it to dissolve many solutes. Okay. All right, here's another vocabulary word, hydration. Okay, it just means a salt dissolving in water. I mean, this prefix, HYDR, hydrate, hydro, Okay, that always is the prefix for water. Okay. And here's the thing, okay? When I say water will dissolve most things, let's be specific. Water dissolves most ionic salts, not all, but most. Water can also dissolve, and when I say non-ionic, what I really mean is covalent solutes, as long as that covalent solute is a polar molecule. Okay? So water can dissolve not everything, but many, many things, most things. Now I realize, guys, there is a lot going on in this picture. Let's break it down into sort of manageable pieces. Okay? This is representing a cube, okay, a chunk of sodium chloride. Sodium chloride, ionic or covalent? Ionic, okay. So the little purple pieces are representing sodium ions, and the little green pieces are representing chloride ions. And I want you to focus on these two pieces of the picture right here. Can you tell me, well, first of all, let me just say what this picture is illustrating is the process of something dissolving. And that's what that word solvation means. It just means the process of dissolving. But let's focus right here. Here's a sodium ion. Why does it make sense that in this picture, right, these are water molecules, why is the oxygen side of the water facing that sodium ion? Think about that. Okay, yeah.
Because opposite charges attract.
Correct. Think about what we just drew. We said that the oxygen side of the molecule is a little bit more negative, and this is a positive ion. As he said, opposite charges attract. So all of the sodium ions, as this dissolves, will be surrounded by water molecules with the oxygen side facing it. And look at this guy. Chloride is negatively charged, so the hydrogen side of these water molecules are facing it. Okay? And this is how something ionic dissolves. Water sort of wiggles its way into this ionic cube and separates the ions. What is presented on the right-hand side is a covalent solute. Okay? In this case, it is the compound methanol. That's a covalent compound. It's one of our alcohols. It is also a polar molecule. Okay? So there's no charges in here, but these methanol compounds are attracted to the water as well. So that's just on an atomic level what the process of dissolving looks like. Okay, here's another vocabulary word, solubility. If I were to ask you for some compounds solubility, guys, I am asking you for a number. Solubility is a number. It's a mass in grams of that solute that will dissolve in 100 milliliters of water. Okay? And those numbers are going to vary greatly. Okay? You're going to get a wide range of solubilities. A solute that is very, very, very soluble is going to have a high number for this solubility. Some solutes we say are slightly soluble. Something like that is going to have a much lower number for its solubility. Okay? Something that is insoluble is going to have a solubility very close to 0. Okay? Let's talk about another vocabulary word. Electrolyte. Okay? I'm gonna ask you what the word electrolyte means, and I bet I can just see it on your faces. What are you thinking? Go ahead and say it. Gatorade. Okay? So Gatorade is not an electrolyte, but Gatorade contains lots of electrolytes. I'm hoping you saw that word in Chem 1. Does anybody remember what it means? It's something that ionizes very well. That's true. Something that it releases a lot of ions into the solution, and because it does that, what can it do?
It conducts electricity.
It can conduct electricity, absolutely. Okay? So guys, when I say a strong electrolyte, it means exactly what she just said. It's something that when it ionizes, it releases a lot of ions. It ionizes very, very well. And guys, if you have a lot of ions, you will be able to conduct electricity very, very well. By the end of today, I'm going to expect you to be able to look at a compound and tell me if that compound is a strong electrolyte or not. So how do you know what are strong electrolytes? Well, first of all, most of your ionic salts, not all, but most, are going to be strong electrolytes. Things that ionize completely. They release lots of ions into the solution. Okay. And when I say these things conduct current efficiently, that means if I were to put a set of electrodes into a solution of, let's say, sodium chloride, we could get a light bulb to light up brightly. Okay. What else is a strong electrolyte? Your strong acids. Okay, there are lots of acids out there, ladies and gentlemen, but 6 of them in particular, these 6, are considered strong acids. Now I want to talk about what this word means, because there's a lot of misconception with this. A lot of people think strong acid means like the most dangerous acids, okay, or the most corrosive acids. And you know, these are dangerous. I mean, these are acids you don't want to mess around with. They will hurt you if you spill it on yourself. But I will tell you guys, the most corrosive, probably the most dangerous acid out there is not in that list. Does anybody know what it is? If you're a Breaking Bad fan, you might know. Do you know?
Is it going to be hydrofluoric?
You got it. Hydrofluoric, HF. That is nasty stuff, like eat your face off kind of acid. Okay, but these are the 6 strong acids. And when I say strong, it means the same thing as it does up there. These are acids that when you put them in an aqueous environment, completely ionize. So take this one for example. Okay, first of all, let's review. What's the name of this acid? Thank you, nitric acid. Okay, when this ionizes into its 2 ions, what do you get? What are those 2 ions? Not a trick question. Okay, H plus and nitrate. Okay, these things ionize very well. I hate to be the bearer of bad news, but ladies and gentlemen, you just have to memorize those acids. Okay, and I've got a little memory trick here on the board. If you can remember this sentence, you can remember these 6 strong acids. Imagine a perfectly clear, breezy summer night. Okay? So I imagine hydroiodic. Perfectly perchloric. Clear, Cl, hydrochloric. Breezy, Br, hydrobromic. Summer, sulfuric, nitric. We've got ionic salts, strong acids. You also have strong bases, okay? And again, strong means the same thing that it did here and up there. Things that ionize completely, you need to know these as well, okay? So what are your strong bases? First of all, your group 1 hydroxides. What's the name of group 1, the family, on your periodic table? Everybody.
Alkali metals.
Thank you, alkali metals, okay? So any alkali metal paired up with hydroxide. So lithium hydroxide, sodium hydroxide, potassium hydroxide, etc. Those are some of your strong bases. These are metals from group 2. Please notice though, not all the metals from group 2 are there. For example, magnesium hydroxide is not a strong base. Okay? And a couple of years ago, I guess some of my students came up with a way to remember this, and I kept hearing them say this phrase, this term over and over again. I kept hearing them say cabasser. What are they talking about? That's not even a word. Okay? Cabasser. Okay? You know, come up with whatever's going to work for you, but you got to commit these to memory. All right? What's the opposite of strong? Weak. Okay? Weak electrolytes. Things that will ionize, but to a very small extent. Things that will release ions into the solution, but not a lot. So you can get current, but not much. Okay? So this is when you would see a light bulb light up, but very, very dimly. You don't need to memorize your weak electrolytes. Okay? You don't have to memorize what are your weak acids. If it's any acid that's not on this list, then it must be a weak acid. Same with weak bases. If it's not in the list, it must be a weak base. So we had strong electrolytes, weak electrolytes. We also have non-electrolytes. Things that have can conduct no current at all. Okay? And let's think of some examples here. All right, I'm actually going to go out of order here. A sugar solution. All right? Doesn't matter what kind of sugar it is. Is sugar soluble in water, first of all? Yes or no? Yes. You know, you put sugar in your tea or your coffee, it dissolves, without a problem. And it doesn't matter what sugar, glucose, sucrose, whatever. All right? But I'm telling you that a sugar solution is a non-electrolyte. Why would that be? I mean, sugar dissolves. So why won't it conduct electricity?
It doesn't ionize.
Right. It doesn't ionize. And why not? Well, let's think back to biology, okay? What's the formula for glucose?
C6H12O6.
Very good. C6H12O6. All right, C6H12O6. Why doesn't that ionize? I mean, it dissolves. What's the problem here? He says there's no ions. How come there are no ions? Think about the formula you just said. It's not ionic. It's covalent. Okay? Covalent things are not going to release ions. But tell me, and this is the last piece, then why does it dissolve? Exactly. Because it's polar. Okay? But just because something dissolves doesn't mean it's going to release ions. Let's talk about pure water. When I say pure water, and I know what you're thinking, like, well, what other kind of water is there? Well, let's think about if I took a sample of water from the faucet over here. would that sample of water be truly just H2O and nothing else? No. Well, what else is in there? Okay, chloride, what else? Okay, metal ions, absolutely. Hopefully not like lead, but maybe. Most pipes, are made of copper. There could be some copper ions in there. What is it that a water treatment facility will put in the water? It's good for your teeth. Fluoride. Okay. So there are ions in tap water, right? But there are so few that I'm not even going to call it a weak electrolyte. Okay, tap water is like the weakest of the weakest electrolyte. You're not going to see it light up a light bulb. Okay, but when I say pure water, what I really mean is deionized water. Okay, we have a piece of equipment in our chemical storeroom, so cleverly named the deionizer. Okay, and all it does is take water from the faucet and remove all of those metal ions, fluoride ions, etc. Okay, so truly deionized water would be a complete non-electrolyte. Okay, so let's get into the math of this. Do you have your calculators? Good. Okay. Molarity, ladies and gentlemen, that is the most common way to put a number on how concentrated or how dilute something is. Let me just refresh your memory on how it's calculated. Molarity is moles of your solute divided by liters of your solution. Another way to say what's in the denominator would be total solution volume. Okay? And let me just show you a couple of things here. If you ever see something that looks like this, a set of brackets around an ion or a compound, brackets around something, ladies and gentlemen, means the molarity of that thing. Brackets mean molarity. Okay? So I would say something like the molarity of this is 3 molar, capital M. Now, some of you with questionable handwriting, you need to be careful with how you write your units because a lowercase m as a unit means something else. And I don't think they taught this to you in Chem 1 because it's a unit of concentration that just isn't used so much anymore. This is molarity. This is something called molality. Okay? So the point is, be very cognizant of the fact that you need to write a capitalized M because a lowercase m means something else. And if you're concerned that your handwriting is not the greatest and are we going to know if it's capital or lowercase, you can always write the units like this. Moles per liter. You can't go wrong with that. Okay? So there's 2 ways to write the units for molarity. Okay? So let's get to some practice. Before we launch into this, okay, the first part of both of these problems should be very easy for you. Okay? This second part might be new to you. Okay, so I just want to show you something here. So for number 1, hydrochloric acid is our solute. Tell me, please, okay, first of all, is that one of our strong acids, yes or no? Yes, okay. And what happens to this acid when you put it into an aqueous environment? What happens to any strong acid? What does this mean? It ionizes. That's the word I was looking for. Okay? So what are the 2 ions that this breaks down into? Okay, all right, be careful. H plus, not Cl2. Cl2 is chlorine gas. Remember what we said. This ionizes. Ions. What's the other ion? Cl minus. Okay. Is that balanced? Yes, it's balanced. Okay. Let's think about if this one is my solute. Okay. Right? Ionic or covalent? Ionic. Okay. Do ionic salts typically ionize in an aqueous environment? Okay. So let's say what those ions are going to be. Tell me. Okay, iron, and what charge does this iron have? Very good, +3. And what's the other ion? Sulfate, okay. Balanced? No, and we need to balance it. Okay, so why did I do that? Well, that's knowing that, how these compounds are breaking down is going to be important when you're answering this second question. Try this. Okay, let's just look at just this first problem if you're having issues with these second parts here. Okay. The first part of number 1 up here, that should have been pretty easy. Okay, or I hope it was. The second part where it says what is the concentration? Remember, concentration just means molarity. What is the concentration of each ion? Well, guys, they gave us the molarity of the whole compound. That was given to us in the problem. Where did I get these numbers? Where did 1 and 1, where did that come from? Look at what's written right above it. Yeah, the equation. These are the coefficients, or let me say it another way, the molar ratio. Okay? And you can do that with molarity. So the ions, because they're all in a 1-to-1 ratio, both of them have the same molarity as the compound as a whole. And again, once I had the molarity for the whole compound, and I'm trying to get down to the individual ions, I just use the molar ratio. Okay, so calculating the molarity of ions, that's something that you probably haven't done before. Maybe some of you have. Okay, but get used to doing that because, when we're talking about dissolving process in solutions, that's something you will need to calculate. So let's move on to the last little topic in this section that I want to do today. And it has to do with the fact that on the AP exam, in the free response section, you are pretty much guaranteed to see at least one question that has to do with lab procedure, okay? Maybe you're asked to come up with the steps needed or what data would need to be collected in order to do this. Or what we're going to look at today is, you are asked to make this particular solution. What steps would you need to, or what would you need to do in order to carry that out? There are some terms you need to know. Okay, the first one is the word stock. A stock solution. That means something, a solution that is relatively concentrated. Okay, now what does concentrated mean? When I say concentrated, I mean there's a relatively large ratio of solute to solvent. What's the opposite of concentrated? Dilute. Yeah. Okay, So a dilute would mean a relatively smaller ratio of solute to solvent. And look at how that relates to molarity. Something that's relatively concentrated is going to have a higher molarity. Something dilute, a lower molarity. Okay? And, you know, we use these terms. I'll give you a very real-life example. When we do labs in here and we need some kind of an acid, I will very often choose hydrochloric acid. It's a strong acid, it's relatively cheap. We will use it a lot this year. And so every August when we start looking at, you know, okay, what chemicals do we use every year? What do we need to reorder for the coming school year? Hydrochloric acid is usually something we have to buy. And when it arrives, okay, it arrives in a box, and what's inside this very, very heavily packaged box is a small bottle of very concentrated hydrochloric acid, okay, which is nasty stuff that you don't want to mess around with, okay? It's a stock solution. Now, tell me this, guys, if I have this very, very concentrated bottle of acid, I'm certainly not going to let you guys use that acid in the lab because it's very dangerous. I'm going to dilute it down to something that's a little safer. How do you dilute something that's very concentrated? What do? Yeah, add water. Or, and more generally, add more solvent, but most often, yeah, add more water. Okay? And so, you know, I have to think about these terms a lot when I'm doing something like that. Okay, let's look at, you know, a situation that you might see on a you know, an AP exam or maybe one of my tests. Let's say that I ask you to make, I'll write it on the board here. I ask you to make a 6 molar solution of copper sulfate, and I would like you to make 2 liters of it. Okay, so I'm doing a lab with copper sulfate. I want it this concentration, and this is how much I need. I want you to look at these 2 pieces of information, a molarity and a volume. What can you immediately solve for? Moles, okay? Moles of what in this case? Copper sulfate. Okay, so I go into the back storeroom here, the stock room, and I find copper sulfate. It's a nice blue powder. And I go over to the balance. That's 12 moles. Balances don't measure things in moles. So what do? Convert it to grams, absolutely. So if this is a test question, ladies and gentlemen, the first thing you would need to show me is that math. How many moles do I want? And let's convert that to grams. Okay, show me the math. Step 1 would be measure out however many grams that is on the balance. That's step 1. Step 2, add it to this piece of glassware. It's called a volumetric flask. You need to know that term, a volumetric flask. And guys, volumetric flasks come in all sizes. Big ones, little ones. Oh, it's so cute. Okay, let me tell you something. Okay, this is like this small one. It's a 25 milliliter volumetric flask. This is a completely worthless piece of glassware. I am never needing to make just 25 milliliters of something. I mean, maybe in a lab setting, you know, in the real world, this is useful, but you know what I use this for? For this moment right now, to say, this is how small they come, and then I just take this and I put it back in the cabinet for the next 365 days. That's what it's used for. Okay? But the point is, guys, so this is a 2-liter volumetric flask. And you'll notice it doesn't have any volume markings on it, except for one. And you may or may not be able to see it. There is a very faint line painted on the neck of this flask. That line measures exactly the volume written on it, okay? So, I add the copper sulfate into my, what size? 2-liter volumetric flask, which this is. And I add deionized or distilled water. And you don't even have to say how much. You just say add it up to the 2-liter line. Done. Okay? So those are the steps for creating a solution. Now, in this case, my solute is solid. And what if it isn't solid? Okay? Like, for example, I told you about how I have to make more dilute solutions of hydrochloric acid. The stock solution is liquid. And guys, I hope we all realize that you can't pour liquids onto a balance. Okay, that's just silly. You're not going to do that. Okay? So, what do? Okay, well, you have to use this equation right here, which I'm pretty sure most of you have used. You know what capital M stands for? Not moles. Molarity, and this is volume. Okay. I want you to think of the left side of that equation as like the concentrated side and the other side as the dilute side. Okay. So let me change the numbers here. So let's say we're doing a lab and I need to make 1 liter of a 4 molar hydrochloric acid solution. I go back into the chemical storeroom and I pick up that stock bottle, and that stock bottle is 12 mole. Okay. Well, I can't let you guys work with 12 molar HCl. That would be a terrible, terrible idea. Okay? So I've got to get it down to 4 mole. We're going to use this equation. Okay? So M1, V1. M1, concentrated molarity. Which one is the concentrated molarity? 4 or 12? 12. Okay. All right. Was I given a volume for the concentrated? No. So guess what? That's my unknown. Molarity of the dilute, meaning the solution that I want to make. Okay. Now, I'm hoping you don't need a calculator for this. 4 divided by 12. Okay, 1/3. And this volume, when I solve for it, what units would it be in? Liters. Okay, so that's 0.333 liters. Well, that number kind of bugs me. I'm going to change it into milliliters. I need 333 milliliters of my stock solution. Okay. So this picture, this is representing the stock solution. Okay. I'm going to use a piece of equipment called a pipette. Don't call it a pipette, that bugs me. Okay. And I'm going to draw out 333 milliliters. And where am I going to take it? I'm going to put it into my 1 liter volumetric flask. Okay, well, here's the problem though. I've just put 333 milliliters in there, but I need a whole liter. So what's going to make up that difference? Water, absolutely. Okay, so I'm going to fill it all the way up to the 1 liter line. You don't have to say how much, with either deionized or distilled water, your choice. So you need to show me the math, you need to tell me the steps, you need to tell me the piece of equipment. And I'll tell you, there are sometimes going to be problems where it's like they almost give you like a word bank, except it's not a word bank, it's an equipment bank. And they'll say, you know, this is what's available to you. And they're going to try to trick you, okay? They're going to put, if we were doing this problem, they're going to put a 1 liter beaker in the list, okay? They're going to put a 1 liter Erlenmeyer flask in the list because they are trying to trick you. They're going to put a 500 milliliter graduated cylinder in the list. That's not what you want to use. You use a pipette, okay? So you will choose from which pieces of equipment, which chemicals to use. Don't fall for their tricks, all right? So this is our last slide today, guys. Let's do a little practice here. And the first thing I want you to notice is that numbers 1 and 2 look almost identical, except for one difference. That word in italics. And ladies and gentlemen, changing that word changes the math. See if you can figure this out. So let's talk out numbers 1 and 2, and let's work out what's the difference. Okay. First and foremost, you got to make sure that you know which set of numbers goes with the concentrated, which set of numbers goes with the dilute. Okay. So we have this set amount of hydrochloric acid, and we're adding water to it. So we're making it more what? Concentrated or dilute? Dilute, okay. So this volume, this molarity is the concentrated side. So I can plug those values in here. What is the concentration? M2 is my unknown. What number should you plug in for V2? Okay, so 0.2685 liters, she says. That's correct. Now let me say one thing about units here. Many of you probably changed the volume from milliliters into liters, and you can do that, but you don't have to. As long as you have milliliters on both sides, then you can leave it in milliliters. Okay? So 268.5 milliliters is for volume number 2. You're combining them. What makes number 2 different? Which variable? M1, V1, M2, V2. Which variable will be different? Yes, sir. V2, okay. What volume should you plug in for V2 in this problem? Kevin, tell me.
250 milliliters.
250 milliliters. When this says is diluted to, that means enough water was added to get up to the 250 milliliter line. Okay, so let me just show you what that looks like. Okay, and the third one, we'll just talk out the steps here. Okay, so between 1 and 2, are the molarities, does it change a lot? No, not a lot, but enough. When you round for sig figs, it does change it. Okay, and let's just talk out the steps for number 3. The math is not difficult in number 3, but you guys tell me. This is the volume of stock solution I need to use, and what piece of equipment should I use to get it? A pipette, okay? I draw it out with a pipette and add it to what? Thank you for saying the volume. A 1 liter volumetric flask. Okay, that's step 2. What's the final step? Yeah. Fill it to the 1 liter line with deionized water. I'm going to stop there.